Okay, so in this video, we're going to have a quick look at this paper here by Selkirk et al. So let me get the paper up and tell you about what the paper's about. Effectively, the paper is asking the question, well, if I see a p-value of 0.05 or a p-value of 0.01 or any other p-value, what's the strength of the evidence that that conveys against the null hypothesis? And of course, there are some assumptions that you need to make, but under a broad set of assumptions, essentially the conclusion here is that you can bound how strong the evidence is against the null, and this is kind of their bottom line here, is that the Bayes factor against the null is never any stronger than this expression here, negative E p log p. But maybe I want to start before that with kind of their illustration, which I think is also really helpful rather than their bound. So their illustration that they basically consider the following setting where they've got experimental drugs. They're testing a series of drugs, D1, D2, D3. So they consider testing a series of drugs and computing a p-value for each to test the null hypothesis that the drug DI has a negligible effect against the alternative that has a non-negligible effect. So they phrase it here in terms of negligible versus non-negligible because some people don't like the kind of null, the point null, that there's no effect statement, because they believe that every drug has an effect of some kind. So testing whether it has no effect is silly. So that's why they phrase it this way. But the truth is they essentially consider the null that it has no effect. Okay, so think of it as no effect versus an effect. And so now they ask the question, suppose one of these tests results in a p-value of near 0.05, let's say. So not less than 0.05, but near 0.05. How strong is the evidence that the drug in question has a non-negligible effect? And so to study this, what they're going to do is they're going to just do the series of tests for a series of drugs, and they're just going to take all the ones that have a p-value near 0.05 and ask what proportion of them are null. And the answer to that question has to depend on some assumptions, right? What proportion are null among the ones that have a p-value near 0.05 will depend on how, what you assume about that series of tests that you're doing, about the drugs and the series of tests. For example, just in an extreme case, if all the drugs were null, if they all did nothing, then all the ones with a p-value near 0.05 would be null, of course, because they're all null. On the other extreme, if all the drugs have an effect, then all the ones with a p-value near 0.05 would also have an effect. So they kind of, so they set it up, I believe they do it so that roughly 50% have an effect and 50% don't to begin with. But there's still another thing that depends on, which is how strong the effects are, and essentially which essentially determines the power of the test. Okay, so the intuition is if you have the intuition is that if you have a test with no power, then the p-value tells you nothing, essentially. If you do a test with no power, the p-value is uniform under both the null and the alternative, and so the p-value kind of tells you nothing. And so among the ones near 0.05, the null will be exactly at the background rate, which is 50% in this example that we just mentioned. Okay, so the power or the effect sizes are one thing, and the proportion of the two tests. So the answer to this question has to depend on some assumptions, but this is that after looking at a bunch of different, varying those assumptions at different ways, what they conclude is that, again, they started with a 50-50 of the drugs for which the p-value was near 0.05, at least 23% and typically close to 50% had a negligible effect. Okay. I think that at least is based on the bound they derived later, and the typically is based on some some reasonable selection of different possible parameters for the power, etc. So so from that, you kind of say, you know, the p-value of 0.05 can never be very strong evidence against the null, because it at least 23% of the ones that had a p-value of 0.05 were actually null. Okay, and the 0.01 obviously is stronger evidence, but it's still maybe the case that 0.01 is not as strong as you might have thought. Like, because 0.01 sounds like, you know, 1 in 100 chance. That sounds like pretty strong evidence against the null. But actually, you know, among the ones with a p-value near 0.01, typically 15% of those were null. Okay. All right. So where's this at least coming from? Well, essentially that's coming from a bound that they derive. I think they state the bound here, and we won't go over the derivation, but they essentially look at what the Bayes factor is for each different p-value, and use that to compute how, you know, there's a bound on the, they bound the Bayes factor, or the likelihood ratio, if you like, and so using that, they can derive a bound for what's the strongest possible evidence against the null that a p-value of 0.05 can give. And I don't want to go over the derivation, but I want to give you an intuition for why there's, you know, why would there be a bound? Why do you expect there to be a limit on how strong the evidence of 0.05 could be? So the way I like to think about this is that you should know that p-values are uniform under the null hypothesis. So, and the way I like to think about it is that the p-value is like your data. So think of someone giving you data, right? Instead of giving you data, they give you the p-value. They just give you the p-value. They say, I computed this p-value. It's 0.05. Okay, and so now your data are 0.05, and you're asking, well, is that evidence against the null or against the alternative? And what you know is that under the null, the p-value is uniform on 0, 1, right? You don't know what its distribution is under the alternative, but for most tests, you expect that under the alternative, you'll see an enrichment of small p-values, right? That's the point of the test, is that under the alternative, you'll tend to see small p-values. So maybe under the alternative, if you do a test that's not very powerful, but has some power, you might see a distribution that looks like that. We'll draw another one in a minute, but let's suppose that we saw that. And then let's suppose not we saw that. So suppose that is the distribution under the alternative. And let's suppose we see a p-value of 0.05 or near 0.05. Then the evidence, the Bayes factor that corresponds to that p-value is simply the probability of that p under h1 divided by the probability that p is 0.05 under h0. Remember, that's just is the likelihood ratio for the p-value, right? Just think about it. The p-value is your data, and you'll get a likelihood ratio here, which will be this height divided by this height, which is obviously slightly bigger than 1 in this example. So the question is, why is it intuitive that there should be a bound on what this ratio can be? And the idea is, well, you know, if you do a very, if you kind of do a very powerful test, well, you might start to do a more powerful test. You might start to see something that looks like, oh, sorry, maybe that's gone through exactly the same point. That was not a good choice, was it? Let's make it go up more rapidly. There we go. So maybe this is a different distribution under the alternative. Get rid of that line. So this was meant to represent a distribution of what the p-value might look like under an alternative if we did a more powerful test, or if the alternative had where the effect sizes were bigger, for example. But remember, the area under this curve has to still be 1. So if we think about making the effect sizes bigger and bigger, let's say this distribution for the null might start to look like, sorry, for this for the alternative might start to look like this. So the point is, there's a limit to how big this, if effect sizes are small, you might get moderate power, and you get this ratio. If effect sizes are bigger, you start to get a bigger ratio here. But effect sizes are really big, actually the Bayes factor at 0.05 starts to become less than 1. Why is that? Well, if the effects are really big, then under the alternative, you actually expect to see p-values much, much smaller than 0.05. So 0.05 becomes very unlikely under that alternative. Okay. So there's this range of things where, at first, as you introduce some modest effect, maybe if the effects are modest in size, you might expect p equals 0.05 to be slightly more probable under the alternative than under the null. But in settings where there are really big effect sizes, actually you don't expect to see p equals 0.05 at all. You expect p to be smaller than that. And so seeing 0.05 becomes evidence for the null. And so that's the intuition for why there should be a bound here.